Okay. So, good morning. Good morning, everyone. Today we're gonna discuss about some fundamental things that you will need in the rest of the course, and in particular we will be talking about the foundation of thermodynamics in the first hour, maybe even more than the first hour, and then in the second part how to convert heat into electricity with steam cycle. And I remind you that there will be some, to keep the attention up, especially on Monday morning, there will be some quick questions, some quick calculations also to make. So the website is always the same as last time, responseware.eu, and you have the code ME-409EC to log in. So actually, let's start with one question. I would like to understand, just to get an idea, how it is. If you can try to grade from 1 to 5, what is your experience with thermodynamics? Starting from, let's say, 5, it's a very solid knowledge. 1 is basically you have never done it before. And then keep the system open because there will be some other little question, 2 or 3 during the course. Okay. Did everyone answer? Still someone who's okay, so let's close the poll. Okay, so 50% of you studied it in the past and they need some revision, so that's good that we have this lecture, I would say. 2% knows everything, so it's anonymous, but we expect 2 6s at the exam here. Here, the goal of this lecture is to do to remind you about the key concept of thermodynamics. I try to make a selection in order just to highlight the key things that you need during this course. If you're not familiar at all with thermodynamics, you might find this lecture quite difficult. So don't be excessively scared. We can go over these topics once again in the next in the next lecture, because this is the foundation on which you will need to build the rest of the course. So the kind of question that thermodynamics allows us to answer are the ones that are here. For example, we can know what is the energy efficiency of a cycle given a heat source at a given temperature. We can know how much electricity or work we can produce, and it can help us also evaluate the quality of the design of energy conversion systems. And also, I don't know if you remember this episode of The Simpsons. There was a time in which Lisa built a perpetual motion machine, and we will be able to know which kind of perpetual motion machine it was and why Homer was so angry at her for building it, and stating that because she was violating some of the laws of thermodynamics we will see today. So you see that it's not only theory, there's also application. So I will start with some 2-3 slides with some key definitions that you need to know, important definitions that you need to know in order to understand the rest. And then we will see the 2 main laws of thermodynamics, the first and second law. And at the end, I will have a summary which will give you the key concept that you need to remember for the rest of the course, and also to follow the next lecture and some applied examples. So let's start with some definition. So in general, when we talk about thermodynamics, it was started historically as the science of studying heat, let's say, When we talk about thermodynamics, the main concept is that we will refer all the time to a system. So a system is a region of space which is delimited by a thermodynamic system is a region of space which is delimited by boundaries. We separate this system to the rest of the universe. And there are three types of systems that you see in this lecture. There is an isolated system which have no exchange with the rest of the universe whatsoever. There's closed systems which allow only exchange of heat and mechanical work with the external world. So we indicate here heat with Q and mechanical work or electricity with E. And then there are open systems that are the most interesting for us that exchange with the external world mass, heat, and mechanical work. So there are some conventions that we use. Normally, we indicate with the plus quantities that are entering in the system with the minus quantities that are leaving the system. We indicate with a capital letter full quantities, while with a small letter we indicate specific quantities. So, for example, energy per kilogram. And we use a dotted letter when we want to indicate a flow. So, in this case, a rate, let's say. So, for example, energy will have not a dotted letter, while power, which is a derivative of energy over time, will have a dotted letter. And then we define that a system is an equilibrium when the system properties do not change unless there is some external action. And there is something that you already know. You know that if there is no accumulation in the system, the law of Lavoisier tells us that within a system we have the mass balance. So this is something that we know prior to introducing the law of thermodynamics. Then, when we define a thermodynamic process, what do we mean? It means switching from a state of equilibrium to another state of equilibrium of the system. And these kind of processes, which can be either reversible, so let's say infinitely slow, this is theoretical processes, ideal processes that we need to study, but they cannot happen in reality, or irreversible, which match what we have in reality. And then another important concept is the concept of a cycle, which is when the initial and the final state of the system are the same. So we do a series of processes to go back to the initial state. Another important definition is that we have to make a distinction between state variables or state functions and process functions. So the key difference between the two is that state variables such as temperature, pressure, internal energy, mass, and so on, they can be calculated only by checking the initial and the final state of the system, as you see here. Whereas when we have process functions, such as heat and work, we cannot calculate them based only on the initial and the final state. We need also to check what happens in between. So these are, and finally, the last definitions that we need is that we need to define what work and heat are. Especially, we will use later in the remaining of the lecture this equation up here, which basically comes from the Newton laws of physics that says that when we define a mechanical work, we can always represent it as minus a pressure per times a variation in volume of a system. So I just gave you these brief definitions because this is the vocabulary I will use in the rest of the presentation, and I will anyway go back to this definition to clarify some points that I will recall them. But anyway, I also prepared these slides with the idea of them being your lecture material. So there is a bit of text in that, so that when you study them at home, it's a bit easier to go and understand the concept. So let's now start with the laws of thermodynamics. So we have two laws. We start from the first one, even if first and second is not probably the correct terminology in the sense that they were developed more or less at the same time during the 1800s. And the first one, in reality, is relatively simple when we look at it today, because it's a concept that we generally know. With a sort of simplification, we can say that the first law of thermodynamics is the energy equivalent of the mass conservation principle by Lavoisier. So you know that Lavoisier said that mass is never created nor destroyed; it's just conserved. And the first principle tells us the same, but replacing the word mass with the word energy. So if you want to think to it in a very simple way, it basically tells us that as in a bathtub, the level of water is the difference between how much water comes in and how much water you take out. Similarly, the first principle of thermodynamics, in a very simple way, tells us that the delta of internal energy of a system is the difference between how much energy we give to the system and how much energy we get from the system. So looking at the formulation, let's start first from a closed system. So if you remember before, I told you that a closed system is a system that exchanges with the rest of the universe only heat and mechanical work. And back in the 1800s, when the first principle was developed, it was not clear what was the relation between heat and work. Like, people could see the two phenomena, but it was not clear what the relation was. So what they could observe is that if we define a property that we call internal energy of a system, and which is proportional to the variation of heat and work in the system, what in experiments people found out is that over a cyclical process, which we indicate with that integral with a circle, the overall amount of heat and work that we have goes back to zero. So the exchanges that we have of work and heat will finally balance to zero. And what does this mean in practice? So first, it means that heat and work are closely related. So this was a major discovery in the 1800s because people understood finally that this heat and work, they had a relation between them, and actually work can be converted into heat and heat could be converted into work. And this is a key concept in thermodynamics because it allows us then to produce work and produce electricity in all the systems that we will see today. It also tells us that the internal energy U that we define up above there is a property of the system. So is a state function. It depends only from the initial state and the final state. And it tells us that energy cannot be produced. So what you will use during the course various times is the final relation here. So the first principle tells us that in a cyclical process, energy is conserved. This means that all the heat that goes all the heat that enters in the system minus all the heat that leaves the system plus the work that enters in the system minus the work is equal to zero. So this is something that could seem to us quite obvious today, this conservation principle, but it was not in the past, and is a key relation that allows us to understand a lot about thermodynamic processes in general. So, as I told you, when we look at the real world, we don't have often closed system. What we are interested in is working on open system. So to pass from closed system to open system, we need to introduce a new concept, which is the definition of enthalpy. So enthalpy is simply defined, this is just a formula that we can define, is the relation between state variables. So it's the sum of the internal energy of the system plus the multiplication of pressure per volume. And this is something that we need in order to pass from the closed to the open system. So here I show you that by doing some mathematical derivation, so for example we can replace the first principle inside this equation by saying that U is equal to delta Q plus delta E. We can do this differential of pressure per volume. And here I show you that with true relation we can get to a formula that you probably have already seen in your courses of physics in the past. Basically, this formula allows us, when we heat a fluid at constant pressure, it allows us to calculate that the amount of heat is equal to the amount of enthalpy that we exchange in this process. So we can define the specific heat of a fluid, and we get to this formula that you probably have already used in the past, which is that when we heat the fluid, the amount of heat that we transfer to the fluid is equal to the mass of the fluid times the specific heat times the difference in temperature. Okay, so this is the first derivation that we have, that we actually use in everyday thermodynamics, let's say. This allows us to pass to the key results and the key formulas that you use during the course, which is that in real applications, in reality, as I told you, we work with open systems. So we work with systems that exchange also mass with the rest of the universe. So now I put you here some derivation, but I don't put the full one. What we see is that for an open system, we have a similar relation to the one that we have below. We know that the variation of heat and work in an open system is equal to the variation to the variation of mass, so the mass which is actually passing through the system at a given time step, times the difference in enthalpy from the final state to the initial state. And in case, if we have it, also the kinetic energy and gravity. So the first principle for open system is very similar to the first principle for closed system. If you remember, the first principle for closed system was basically telling us. So let me write this thing on the blackboard, maybe, so maybe it's clearer. So if we have a closed system, what we know is that the total exchange of heat plus mechanical work is equal to 0 if we have a cycle, if we have a cyclical process. Whereas, if we have an open system, we have that the variation of heat plus the variation of work that we have over a given process from 1 to 2, for example, is equal to the total mass, to the mass flow passing through the system, if we're talking about power, times the difference in specific enthalpy. So at the end of the day, these are the two relations that we need to remember from this first principle of thermodynamics. And in practice, so when you look at the system in practice, and you'll see in all your exercise, at the end of the day, there are some difficult formulas and formulations there, but at the end of the day, the general formulation that you should remember for the open system is that everything, if you have no accumulation of internal energy in the system, everything that enters also has to leave. So as I told you before, the first principle of thermodynamics, you can really think it as the bathtub of water, which if you don't have any variation in the water level, then everything that enters has to leave. So this equation tells us that, once again, the total amount of heat, the total amount of work, and the total amount of, let's say, energy contained in fluids entering in a system will also have to leave the system if there is no accumulation. So now I show you a little example, and I will ask you to make a very quick calculation, and you have the answer there. So let's consider a very simple application, which is the cooling of a gas. Let's see how this formula is used in practice. So if we're cooling a gas, if we're cooling something, we don't have any production of work, so work here goes away, it goes to 0. We have only that the difference of heat is equal to the mass flow times the difference in enthalpy. So we simply apply our equation for an open system. And I showed you before that the variation of enthalpy in the system is equal to the specific heat times the difference in pressure. So finally, we can do some derivation. And what we obtain is that we get to this quite famous formula that you probably have used before, that the total amount of heat that we exchange in a system is equal to the mass flow times the specific heat times the difference in temperature. So this, which is a formula you probably have already seen before, is a consequence, is a result that we can demonstrate from the first principle of thermodynamics. And now I ask you to do a quick calculation. So try to make this calculation. How much is the amount of heat that we need to give to a system, to a fluid, which has a mass flow of 18 tons per hour, and I report here the specific heat of water. If we want to increase the temperature of a fluid from 10 degrees to 50 degrees. So with this, the only difficulty that you have is basically about unit conversion, and the rest should be okay, I think. So I wait like another 30 seconds, and then because I move to the slide where you can answer, because I cannot do that in the other way. Are you all good? Can I pass to the answer? Or raise your hand if you want a second more. Yeah? Okay. So wait, in the meantime you can start already replying. Huh? So you can reply with so here I'm asking you how much is the total amount of heat we need to heat that fluid from 10 to 50 degrees. Okay, you all good? Anyone still needs time? Okay, so let's close. Okay, so apparently there was a mistake on the last answer, which, if I'm not wrong, I think I created all these answers in order to think of a possible mistake that you could make in the calculation, if I'm not wrong. So probably some of you did not convert 18 tons per hour into kilogram per second. So make sure that you take care of what the units are. And actually, I can give you a little suggestion when you are at the exam, how to always do unit conversions. Maybe I can show you to you here. So let's look in this case. If you want to be sure not to be wrong, in this case you have to convert 18 tons per hour. So you have to multiply this. You can multiply this unit always by 1. So, for example, you can say that 1 ton is 1,000 kilograms. Okay, so this is 1. And you can say that 1 hour is 3,600 seconds, right? So this is a way not to do mistakes in general when you do unit conversion. And so to get it, you have just to divide 18 by 3.6. And you get to 5 kilograms per second. So if I'm not wrong, the 25% of you which gave the other reply, used the 18 instead of the 5 kilograms per second which you should have used. Okay. So let's now define what the energy efficiency is. So as I told you, in summary, what the first principle of thermodynamics tells us is that energy is conserved. So the final equation that you will need to remember is this one up here. So here we can define what is called the first law efficiency, also called as energy efficiency, sometimes thermal efficiency. So the first law of thermodynamics tells us that the energy efficiency of a cycle is calculated by simply compare what you get from the cycle. In this case, what you care about is to get mechanical work out of a cycle, and what you pay for. And what you normally have to pay for is the heat that you have to give to the system. So the first principle efficiency is very simple to calculate. It's simply the ratio between the work or electricity that we produce out of a given cycle and the amount of heat that we have to give to the system. So if we make the example of a power plant, let's imagine a standard power plant. In this case, it could be, for example, a coal power plant. If we have a given amount of energy input from a fuel, which is in this case 1000 megajoule, we produce 350 megajoule of useful work, of electricity or mechanical work, and we waste 650 megajoule of heat. So you see, the application of the first principle is relatively easy. Basically what it tells us is that everything that goes in goes out. So Q plus equal the sum of E minus and the Q minus. And the first principle efficiency in this case is 35%. So, summing up, what do we know from the first law of thermodynamics? The first law of thermodynamics gives us a key result, which is that work and heat are equivalent somehow, even if it's not correct to use this word, sources, and we can convert one to the other. It tells us that we cannot produce energy, and it tells us that perpetual motion of the first kind is not possible. Actually, Lisa, when she built the system in the Simpson episode, she built a machine that was running faster and faster. So this is a machine that produces energy, which is called perpetual motion of the first kind. And already the first law of thermodynamics tells us that this is impossible. It tells us basically that everything, that input equals output. And then we define the first law efficiency, which is basically the ratio between the amount of work that we produce in a cycle and the amount of heat that we give. And as I showed you before, this is a very commonly used way of measuring processes. You also see that it's not so precise in the sense that this value, in some cases, such as when you study heat pumps, can be higher than 100%. So, as we will see in the next in this next slide, there are better ways to account for the efficiency of a process than the first law efficiency. But you have to know this one because this is the most used in general. When someone tells you this is 30% efficient, they mean it's 30% efficient according to the first law. At this point of the theory, so at this point of the presentation, it's still possible though to have what is called perpetual motion of the same kind, of the second kind. So it's still possible that when we have a cycle, we can convert all the heat into mechanical work. So at this point, we can still have ideal or reversible processes, and we can also produce work if we have only one heat source. And that's where the second law of thermodynamics comes in. But before switching to that, I want to see if you have any questions about the first law, and then we can pass to discuss the second one. Is it all clear, or all very confusing? One of the two. Okay. So moving to the second law. The second law basically, tells us this, that if the first law tells us that we cannot win the game, we cannot produce more than we have, so we cannot produce work or energy out of nothing, the second law tells that we cannot even break even. So it is impossible that if we have a given amount of heat available, we can convert all that heat into mechanical work. And that's where the second law enters. So the second law tells us that the variation of entropy of any thermodynamic system caused by internal processes can only be positive or zero, and is zero in case of a reversible process. So here I introduced the formulation, which basically tells us that the amount of entropy generated by internal forces, so the irreversibilities, are always greater or equal than zero. I introduced the equation like this, even if I'll show you only later how this S is derived, but this is basically what the equation says. And just to do a little digression on this, you might know that in fundamental physics, in modern physics, the fundamental equations that have been discovered over the years do not have the time variable inside. So modern physics tells us that time, as we think about it, does not exist. If you go and check all the key equations, the general relativity of Einstein, the Maxwell equations, and so on, you don't have this absolute and universal time, but you have a relative time. And actually, there is a very interesting book that I recently read, and I recommend also to you in case if you're interested. There is this quote that I put there, telling that actually this equation is the only equation in modern physics that knows the difference between past and future. So it's the only equation that is called the equation of the arrow of time. It tells us that the process can only happen in one direction and not the other. An egg can only break. You cannot have a broken egg going back to the state of equilibrium. So things tend towards disorder, let's say. So this is a very important equation. And as the first law, also the second law comes from observation. So we cannot prove this law. The only thing that we know is that nothing has ever happened, or we are never able to show that this law is wrong. And that's the case with most laws of physics. So the second law of thermodynamics can be formulated in two equivalent ways. There are two formulations. The first one, they are equivalent. The first one tells us that it is impossible to build a machine that operating with a cycle that converts all the amount of heat that we have into mechanical work. So there is always some degradation, there's always some losses. And then there is a formulation of Clausius that tells us that it is impossible to build a machine that transfers without the addition, so that it is impossible to have transfer of heat from a cold source to a hot source without putting energy in the system. So heat can naturally flow from hot to cold. And actually, these machines that we talk about in the second principle, that transfer heat from a cold source to a hot source, are called heat pumps. And these are we don't talk about them in this lecture, but you'll see them in the next lecture. There will be a lecture about Francois that tells you how this system works. So, what does the second law of thermodynamics tell us? It tells us that heat does not flow spontaneously from a cold to a hot body. It tells us that we cannot transform completely heat into mechanical work. And so we cannot have reversible cycles, ideal cycles. There's always some losses. We cannot have perpetual motion of a second kind. We cannot have a machine that goes on forever without continuing to add energy. And another consequence is that if we want to produce work, we need two heat sources. We cannot produce work if we have only one heat source. Take care that this equation this principle does not tell us that we cannot convert all the work that we have into heat. So this equation also tells us that work is a form of energy that is more precious, more of higher quality than heat. And you will see this concept of quality in the next slide. So a fundamental result of a second law is what is called the Carnot theorem. So Carnot was a thermodynamicist in the 19th century, in the 1800s. He brought some of the major advancements to thermodynamics. And his main result is that he defined what is the maximum possible efficiency of a cycle. So the key result that Carnot had what this theorem says is that if you give me two heat sources at two different temperatures, so hot and cold temperatures, the maximum efficiency of a cycle that operates between these two temperatures is the efficiency of Carnot, is what we called here the theta Carnot. So if we have a cycle operating between a hot source at T hot and a cold source at T cold, the efficiency, the maximum efficiency of this cycle in an ideal reversible case is calculated by this equation. So it's 1 minus the cold temperature minus divided by the hot temperature. So this is the what is called the Carnot factor, and it's very important because it allows us to calculate what is the maximum theoretical efficiency that we can obtain from a cycle. Two important notes about this equation. The temperatures in this equation are in Kelvin. So if you use this equation with degrees Celsius, you will be wrong. And it is important to note that it's a very powerful equation because it depends only on the temperature. So if we have any two heat sources at two different temperatures, we want to calculate the maximum efficiency, we have to use this formula. So just to verify that you're still there with me, try to make this little calculation here. So we have a heat source, we have 100 kilowatts of heat available, and we want to convert it into electricity with a resource with a hot source at 150 degrees and and we work with the ambient temperature, which is at 20 degrees. So what is the maximum amount of work that we can produce ideally from this source? Again, I leave you the slide here for 30 seconds so you have the formula there, and then I move to the answer. Okay, so I move to the answer. Are you still calculating? Raise your hands if you are. Okay, so I give you some seconds more. Okay, so I close the poll. Okay, very well. So again, we have 60% correct. So the answer is here. If we want to know the maximum electricity we can produce from a cycle, we just have to multiply the amount of heat by the Carnot factor expressed in Kelvin. So remember to convert the temperature to Kelvin if you have to make this calculation. Okay? So the Carnot factor allows us to define a very important concept, which is the second law efficiency, which is also known as exergy efficiency, or sometimes also Carnot efficiency, although I like less this definition because it can be confused with the Carnot factor sometimes. But so what is the Carnot efficiency? Yeah, exactly. I just told you that. I prefer to avoid this term. What is the second law efficiency? The second law efficiency tells us how well we design an energy conversion system. It compares the maximum, the work that we're actually producing with the system, with our power plant, compared to the maximum theoretical amount that we can produce if we were using a Carnot cycle in a reversible process, okay? So the formulation is this one. It's basically the amount of work that we're producing divided by the heat multiplied by the Carnot factor. And this is an important concept because it gives a value to heat. So now you understand what I was referring to before when I was telling you that heat has a value which is lower than work. Why that? Because the value of heat depends on the temperature at which it has, at which we have it. So for example, if we have heat at 1000 degrees, it's much more worth it than heat at 100 degrees. And for example, if we have heat at ambient temperature, let's say the heat that we have in the lake. The lake is a great source of heat at 25 degrees, but or at 20 degrees, let's say. But out of the heat, we cannot produce anything because it's at ambient temperature. There is no potential of temperature difference. And this comes from the second law of thermodynamics, not from the first. So to sum up what we discussed about in this first part, and then I'll take another 5 minutes to finish this section before the pause. If we have a cycle operating between two temperatures, a hot and a cold temperature, we can define three main things. The first thing is the most simple to calculate, is the first principle efficiency. So it's the amount of work that we produce divided by the heat input. The second thing we can calculate is the Carnot factor. Carnot factor tells us it depends only on the temperature, and it tells us what is the maximum amount of work that we can produce if we were using a reversible cycle, a Carnot cycle, ideal, let's say. The first thing that we can calculate is the second law efficiency, which is the ratio between our actual cycle, how much work we are producing, and the maximum. So the second law efficiency tells us how well our system is designed, and normally the value of a second law efficiency, of exergy efficiency, is about 45 to 55%. So it means if you are closer to 1, it means that as an engineer you are doing a good job, you are reducing the losses, you are reducing the friction in the system, and so on. So this is this is the concept of exergy. As I told you before, the first law efficiency is has sometimes an ambiguous definition, or at least can be problematic because it has values that can be higher than 100%. The second law efficiency it has an advantage because it defines efficiencies which are always lower than 100%. And it allows us to compare also more complex systems such as cogeneration, three-generation system, heat pumps. With the second law efficiency, we have a basis to compare all these systems. And let me tell you some minutes more to finish this part, because the second part will be a bit shorter. So now I have the last calculation for you, which is so you remember that before I showed you this power plant. In this power plant we have an input of 1000 megajoule in this case, we produce 350. So we know that the first low efficiency is this one, is 35%. My question is, what is the second low efficiency, knowing that the system works between 1000 degrees and 20 degrees? So the only thing that you don't have there that you might need for the calculation is remembering that the Carnot factor is equal to 1 minus T cold divided by T hot. Okay, so I move to the answer. Okay, raise your hand if you need a bit more time, or if you... Okay, so some seconds more. Okay, let us close this poll. Okay. So you are either, so there are two options. Either you are really following, or you have the slides on Moodle and you are checking the next answer in the next slide. So I hope it's the first one. So you see, the exergy efficiency of this power plant is 45%. It means, as I told you, this exergy efficiency is normally between 45 and 55. So in this case, the first law efficiency is 35. The maximum we could have, the result of the Carnot factor, that calculation that you did there, if I remember well, was something like 76, 77%. So that's the maximum we could do. If we could do a reversible cycle without friction, without losses and so on. The real efficiency, so the exergy efficiency is 45%. It means that we are only getting 45% of what we could do in theory. So now, before the pause, I just show you where this entropy comes from. So I showed you before only the equation. I started with the equation of entropy, but where does that S come from? So to do this, there are some slides which I put advanced there. So in the sense that if you found difficult what we discussed up to now, you might want to check this at home better. But let's say the conceptual thing to demonstrate where entropy comes from is that we can prove that the ideal efficiency of a cycle is equal to 1 minus T cold divided by T hot, which is also equal to this ratio between the heats, okay? So the conceptual way to get to this formulation is that every ideal process can be represented by very small Carnot cycles. So every real cycle can be approximated by an infinite number of small Carnot cycles. And for each of these small Carnot cycles that I put here, you add the sum of the heat divided by the temperature for the hot source and the cold source is equal to 0. So if we extend this formulation, so if we go to infinite number of cycles and we do the integral, then we have the theorem of Clausius. The theorem of Clausius tells us that over a reversible cycle, it's a corollary of the second law. We can demonstrate it if we assume that the second law is correct. We see that the total amount of heat which is exchanged at a given temperature is equal to 0 for a reversible cycle. If we have a relation like this, it means that in the same exact way that we did for the internal energy, we can define a state function of the system which is dependent only on the initial and the final state. And that's where entropy comes from. So entropy, equivalent in the same way in which we defined internal energy before, is the state function that corresponds to the variation of heat that we're exchanging in a system over a reversible cyclical process. And so if we look at the real world process, as I said, real world processes are irreversible. We see that the second principle tells us that in every real world process, we are losing heat. So there is an amount of heat that in every real world process, we lose by the transformations that we have. And so this is the more complex formulation of the second law efficiency, of the second principle. It tells us that for a reversible cycle, the amount of, we don't have losses of heat, so the amount of heat that we exchange over the system in a reversible cycle is equal to 0. If the cycle is irreversible, we have an amount of entropy increase which is greater than 0. So we lose heat by friction, by leakages and so on. So this is where the entropy comes from. And based on that, we can derive in this way we can derive the famous Gibbs relation. So we can derive these two formulas, which we will use also later. that are valid for every reversible and irreversible process that relate the variation of internal energy and of enthalpy to the amount of heat. So if you remember the first law, it was telling us that the amount of internal energy is equal to the amount of heat minus the amount of work that we produce. Although this relation, this one, to be rigorous, we could use it only for reversible processes, but this formulation still holds. So with this, I let you there an example that you can check also at home. It basically shows you how we can apply these equations in an isolated system to show that actually the amount of entropy increases when we're considering an isolated system and we're only looking at internal processes. And let me summarize what we learned in this lecture. So, in the second law of thermodynamics, you remember that I was telling you before, with the first law we could still have perpetual motion of the second kind, so we could still convert all the mechanical work into heat. The second laws tell us that in the real world there are irreversibilities. Entropy increases, so we cannot have perpetual motion of the second kind. And if we want to generate work, we need to have two heat sources at the different temperatures, and we will not be able to convert it entirely from entirely the amount of heat into the amount of work. And additionally, we define two main efficiencies. The Carnot factor, which gives us the ideal maximum efficiency that we can obtain out of a cycle, and the second law efficiency that tells us how well we design our energy conversion system. And as I told you, it is more rigorous than the first law efficiency because it always defines values that are between 0 and 1. So to close this part, let's recall the first law tells us that energy is neither created nor destroyed, but is only conserved. And this equation is the one you'll be using often in this course and the exercises, telling us that everything entering a system will leave the system if there's no accumulation. The second law tells us that there is, in every real process, there is irreversibility, there is entropy, there is an entropy increase. So you will always lose something out of a real process. And then there are, given any cycle, operating between the high hot temperature and a cold temperature, we have three efficiencies that we can calculate. The first law efficiency, the Carnot factor giving us the maximum theoretical efficiency, and the second law efficiency which tells us how well we are designing the system. So going back to the question that I had posed at the beginning of the lecture, if we want to answer what is the energy efficiency of a conversion cycle, we use the first law efficiency. Okay? So we compare what we get to what we spend, and we get that. The second one, if we have only one heat source on sink, how much work can we produce? We can produce no work, and that is what the second law of thermodynamics tells us. The third one, what is the maximum amount of electricity that can be produced by a geothermal resource at 100 degrees C? So this one, again, we use the second law, we use the Carnot factor, and here I added also an exergy efficiency compared to the, because before I asked you to calculate the maximum theoretical amount, which was 30 something kilowatt. The real amount, if we account also for an exergy efficiency of the process, will be around 17. And then, if you want to evaluate how well you design your energy conversion system, you use the second law efficiency, which tells you the ratio between the real efficiency and the theoretical one. So, I took 10 minutes more, so I would say in the next lecture we can start at 11:25, and it will be also a bit shorter because then in the third hour today you have also the first exercise. So if you have questions, so anyway I'm here also for 10 more minutes. Okay, so I will start here by showing you the exercise that you will be doing today, connected to the first lecture, the thermodynamics lecture. So you are given a geothermal cycle, and you are given a geothermal heat source that has a given mass flow, and that exchanges with the cycle. So the reasons with an energy conversion cycle. So you have the water, the black line is the water coming out from the geothermal source, and the purple line is the fluid inside the energy conversion cycle. And you see that the fluid is first heated, then you have a turbine to produce some more, then you have a condenser and you have a pump. You'll see today how cycles work, but this first exercise will allow you to make some calculations, applying the formulas of the first and second law efficiencies that we studied today. Okay, so later there will be here Xian Li and myself, and Louise, the other assistant, is today sick. So we will be here starting from after this lecture, so this lecture will last about 40 minutes or so, until 1, in order to assist you with the exercises. And I remind you 2 things. So next time, at the end of this lecture, I will give you another exercise that we will start solving next week at 10. So if you remember, I told you last week that we make this experiment of starting with the exercise for the first hour next time, and the lecture will start instead at 11 or 11:15. Actually, we'll start it at 11, so we finish a bit early. So try to be here around 10:15 for the exercise next week. And another thing, before passing to the new lecture, is that remember that by maximum next week, you need to be enrolled in a group. So there is, if you go on Moodle, there is a link to a Google Doc spreadsheet. Make sure that you're part of a group. If you are not part of a group, if you don't have friends, then you can contact also other people or put your availability there in a part of a sheet, or also try to come to class and organize. But it's quite important that you organize in groups, because actually, so we are deciding if the project will start next week or the week after, because the main responsible of the project is Louise, who's now at home sick, so we are seeing that. So anyway, both times be here at 10:15, because one of the 2 times there will be a 20-25 minutes presentation of the project. So it's quite important that you're here to follow that. Okay, so please register to the group, and let's start with the second part of the lecture.